So, Gerard, thanks again for taking time out of your Friday to come and talk to us at the NGN and our member base. So, by way of introduction, Gerard Ledwich is a Professor of Electrical and Power Engineering at the Queensland University of Technology, or QUT. He's a Fellow of the Institute of Engineers Australia and a Fellow of IEEE. Gerard has held positions at the University of Queensland, in the Queensland Electricity Commission, and at the University of Newcastle. Gerard's current position is Principal Research Fellow at the Queensland University of Technology, and his research interests include control systems, power electronics, power systems, condition monitoring, and distributed generation. Gerard is extensively published and is on the editorial panel for the Journal of Modern Power and Clean Energy. So, Gerard, I'd like to formally welcome you, and again, thank you for taking time out of your Friday. And I will hand it over to you to start the presentation, if I can make you the presenter. So now you should have access, Gerard, to share your screen. Fantastic. We have that single presentation slide, and that's coming through clearly.
Excellent. So thank you all for attending. It's an interesting area of controls, is looking at the development of new power electronics. Sometimes you get the impression that the changes in the power system are all a big nuisance and you wish they would go away, but I think that there's a lot of powerful work that can be done by knowing how to integrate them with power systems, how to control it all. This all started by a comment from someone from PowerLink. He said that they were going to put in lots of PMUs and to monitor machines and inverters. And I thought, yep, I know how to monitor machines. I know what oscillation modes of machines are all about. But I really don't have a tool to investigate modes of oscillations of inverters. And that sort of started the exercise. Then along the way, I was hearing about bunches of inverters in northwest Victoria that had to be scaled back in their power output because of oscillations. So that's part of the motivation for the development. The other thing that was learned along the way was modeling. That inverters is an area where we haven't traditionally had a big range of models available, and so if you wanted to validate a particular company's design, you really should just do a complete full state model of the system. And I'm saying, well, in almost every other area of engineering, there's a graduated level of modeling that's appropriate. The example that I like is the model of a transmission line. So if we were doing lightning studies, we would do a traveling wave model. If we were dealing with voltage rise issues, we might use a pi model. While for stability, we might represent the line just as a 50 Hertz inductor. So that's well-established tradition of what modeling is appropriate for the questions being asked. But for inverters, yeah, it's not been traditionally as clear. You know, what sort of detail do we need to be able to come up with our control design? So we're all aware of the detailed models that we could use of synchronous machines. We could be modeling all different aspects of things, but the question then is, well, what's the question? What is the most important thing? I'm just giving a bit of a teaser here of the levels that we're going to go to in talking about the models of inverters. So the first one represents the inverter just as a phasor. It's only talking about their 50 Hertz impact as magnitude and phase. All line impedances are complex numbers. So that's a very simple way to understand the world. It gives you a certain comprehension of how things work. Switched average models use differential equations for all inductors and capacitors in the system, but we don't go into the details of the switching state of the inverters. We treat them as ideally producing a particular voltage. But it does give us a lot of control tools, because a lot of these tools are linear, and so we can come up with good designs for controls. And at the last level of detail is full PWM models, where we represent every switching edge. But generally speaking, we don't have a lot of design tools for shaping how they would control systems. The next little teaser, I guess, is when talking about synchronization of inverters, that traditionally we've synchronized to the terminal voltages. So we're trying to inject current exactly in phase with the voltage at the terminals of the inverter. It's a nice way to do it. It works adequately well for your home photovoltaic system. But when we start to talk about large inverter stations in the middle of the power system, there is a set of problems that start to arise. And so these other two levels of control possibilities are what I'd like to be introducing through this talk. One is to say, well, what's important is to inject current that is roughly aligned with the angle of the voltage vector for the state. So if you're looking only at Victoria, you might say, well, what's the average angle of Victoria? Let's inject any current at that angle. The next one, or the next level of complexity down, is to say, well, my problem is looking at my terminal volts is that every time I make a change, I change the terminal volts. If there's another inverter down the same line as myself, every change that I make, or he makes, affects my voltage. And so that drives the process of instabilities. It complicates the process. And what we're trying to do is to say, well, upstream from me, there is some stiffer voltage sources. There are more reliable voltages I can synchronize to. And so this process is one of trying to come up with a Thevenin measurement to infer a stiffer point. So rather than trying to always just synchronize to a weak section of the network, infer what the strong section of the network looks like and then synchronize to that. So this is just a looking forward based on the different levels of modeling. Okay, why do we go for simple things? So one is the simulation time benefit from a smaller model, that we, rather than simulating a 1,000th order model, we might get away with simulating a 10th order model to answer some of our questions. But that's becoming less critical as computing power expands. But one of the main goals to focus on a simple network, a simple representation, is that we can develop a good control strategy. If we had a model of the power system that had detailed models of every machine, every line, every inverter, any of the control tools that are currently available would find it difficult to say, well, what information is important? How can I come up with a control design when I've got this 5,000th order model to try to represent my system? An example that I like here is when we were starting to work on traveling waves on groups of synchronous machines. That what tends to happen is that there is a concept, there is a process whereby if a fault happens, say, in the top of Queensland, it gradually propagates and influences synchronous machines elsewhere. But to get an understanding that this is really a travelling wave problem, we can represent these, each one of our generators as a simple second order model. Is that the perfect model for the process? No. Does it give you a handle on what's happening? Absolutely. So let's get back to some of the reasons why we want better controls. And the first one is that synchronous machine numbers are being displaced by the economics of renewable energy. And so the amount of synchronous machines available at any given time is reducing, the inertia is reducing, which means that frequency changes are happening more rapidly and the corrections are less effective than they used to be. One of the issues here that we were mentioning before is as there's more inverter power added to a high impedance line, there's more instability, and I was referring to the Victorian generators in that case. We need mechanisms to enhance the stability of conjecture of inverters and to control the oscillations and frequencies in the wider system. So rather than saying, well, the things that we know about and can control are synchronous machines, inverters, just make sure you don't do any harm. And what we need to move to a stage where, look, these are our problems and these are the contributions that you will be able to make into the system. So one of the issues with wide area power systems is oscillations that can develop. This picture here is just showing the Australian interconnected network, and the higher frequency oscillations of local machines are generally well controlled, but there has been a history of less well controlled oscillations between areas, and controlling those and controlling frequency is an important issue for the system as the inverter processes develop. SVCs have traditionally been one of the tools that's been available for controlling machine oscillations, and these in a number of places can contribute to the overall issues of oscillations. Now, when we have a look at a phasal model of the synchronous machine, of the inverters, what we say is, well, we can model the way in which the phase of the injected current changes, the normal process of a phase lock loop to terminal volts is to say, well, we've got a reference for the terminal volts at the moment. We make a measurement of the terminal volts and we find that it's shifted a bit. And what we're going to try to do is to make sure that what we think is the terminal voltage angle is actually the angle we're injecting from. But when we did this analysis, we find that these eigenvalues migrate to the right. And if you're not too far from your history of stability in continuous time domain, you say eigenvalues heading to the right, bad idea, introduces instability. And that's a characterization of what actually was observed in the real system. Here's a simple example of a set of inverters. Here we've labeled them a set of inverters all onto the one bus here, and another set of inverters in a string down the line. And we come up with a simple representation, which is the angle of each one of the machines, and the velocities of each of the machines, the angle of the reference of the phase lock loop for each of the inverters, and its velocity as well. So fairly simple phasal representation. Now, it looks like a fairly simple model. You can, of course, get a matrix version of this. So the vector of all machine angles, the vector of velocities, means that this can represent fairly complex networks. So the simple phase lock loop process generally uses a proportional plus integral controller to make the voltage in quadrature go to zero. There are two states for each phase lock loop and two for each simplified machine. So we're not dealing with something that was really complex. But when we start to write it out, we can say, yep, we can see these four groups of states. Up in this corner, we can see the traditional synchronous machine representation of what's happening. Down here, we see a Ki and Kp, those that are proportional and equal controllers of the inverters. And the main thing to note here is the way in which this term here, which is network impedance, creates positive feedback in the diagonal of the network. So this is instability. This is the reason why it's bad. What can we do about it? So here's an example of the way in which a set of synchronous machine oscillations can engage with sets of inverters. And we can see that the general machine oscillations are happening here, but on top of that, there is a wobble caused by the phase-lock loops themselves. And it's this characterization that's important. So when I'm talking about coming up with a control strategy, instead of inverter 8 trying to do its best to follow the variations of the voltage at its terminals, I'm saying, well, what can we do to have a look upstream and say, let's have a guess of what this voltage is, and then I'll synchronize to that. And that's the essence of the line, what I'm calling line drop compensation. You're familiar with saying, well, I know the current, I know the line impedance, therefore I can infer the voltage elsewhere along my line. And so that line drop compensation concept was the beginning of these control strategies. So this is what I'm speaking of here. And when we start to do that, you can start to see the essence of this reduced oscillation from these inverters, that there's less interaction and more possible to control those interactions themselves. And in general, the system becomes more stable. Now, phase-lock loops are okay, yeah, and you can track phase-lock loops even in weak systems, but one of the problems is noise in the system, that the voltage wobbles around, not just caused by inverters, but customer load changes also wobble the angle that you're synchronizing to, making the entire process of synchronization much more difficult. And so what we're seeing here is a possibly more extreme case of wobbles caused by customer loads, and those wobble the machines and the inverters because of that synchronization process. So this was a phasor level of interpretation, and it gave rise to this idea of a line drop compensation type of correction, and it just does help. Now when we get to talk about specific inverters, we're trying to say, well, this is a three-phase inverter, and yes, this will switch high or low to produce the voltage on this particular phase. The switch average approach says, however we control it, this will then set some sort of average voltage on A phase coming out of this inverter, an average voltage for B and an average voltage for C. But then once we've done that switch averaging, we can then talk about the inverter itself as though it was just a controllable voltage source. And so we can then represent all the power system inductances and capacitances, the filter inductances and capacitances, and come up with good feedback strategies for these inverters. Now, traditionally, a lot of the inverter designs are based on single loop current controllers. The difficulties that I've got is that a lot of the stabilization of these is very heuristic. There's no well-developed control design unless you make them a lot slower than they need to be. And so in this context here, I've tended to adopt the linear quadratic regulator approach for controlling the inverter. controlling it as a current source, controlling it as a voltage source is much the same degree, but it's a fairly automated mechanism of coming up with controls with a guaranteed level of robustness, which is one of the big benefits of the linear quadratic regulators. And here's an example here that we can see different frequencies of background oscillations between the converters, but they're well suppressed by doing our state space averaging designs, that we can come up with solutions. And the solutions can take care of the oscillations even without knowing about them. Now, PSCAD is a very popular process of doing detailed switch modeling of inverters. So the process that I'm recommending is the step one, do the switch average model to describe the dynamics, and then simulate it with the full details to validate the performance. And down here we can see the example of the Kalman filter learning of the phase of the voltage sources that we're dealing with, learning what to track. And so here we've got a local feedback control law that's trying to then be in synchronism with our best guess of what this stiff voltage source is going to be. And so here we've got an inverter model and local feedback to make sure that this is well stabilized. The Kalman filter model to infer from the terminal voltage measurements our best guess of the Thevenin source. So 2 stages. And because we're using a Thevenin model, we can force this model here to be close to 50 Hertz. And so any voltage we infer will be pure 50 Hertz and is much less likely to be interfered with by this other inverter. Typically, the phase-lock loop oscillations were in the range of 6 to 10 Hertz, and the Kalman filter model tends to force this representation to suppress any of these other oscillation frequencies. And the Kalman filter comes up with a representation of a 2-phase model of the bus. You can see the learning of the phase of the bus, learning of the magnitude of the voltage of the bus as time goes on. And this design for the phase-lock loop, the Kalman filter, tells us what the references are. Once we know the references, we can get the inverters to track them. All right, so we've got then a possibility that seems to say that we can get the inverter currents to track terminal volts. We could get the inverter current to track source volts. And this is where we start to go back to traditional power systems analysis and to say, well, if we make the injected current purely in phase with the source voltage, we need to have a high value of the inverter voltage to be able to force that current to flow. If we make the current in phase with the terminal volts, we have a lower value of the terminal voltage than the source volt. And traditionally with synchronous machines, we compromise and we're partway in between. We might tend to go for a situation where both these voltage phasors are of a similar size and the injected current is at an intermediate angle. So when we're choosing what to synchronize to, we need to reflect, well, how much impedance is there? What angle do we really want to have that current injected at? So what's our consequences for a system model if our inverters are able to be synchronized to a local Thevenin? What we say is that all these frequencies directly associated with the way in which the inverters operate are actually can be quite well controlled and at a significantly higher frequency than the inter-machine oscillations. And so if you were trying to come up with a representation at a crude level of what whole of Victoria looks like, you could say, well, there's a few inter-machine oscillations, there's a few inverter to center variations, but by and large, they're all well damped. And as far as we're concerned, we can just represent these inverters as a negative load for the operation at one level of modeling. And so if we had three areas, right, you could think of this as New South Wales, Victoria, South Australia, interconnected. The approach can be that we say, all right, to understand what's happening, let's represent it as a set of machines, an equivalent machine, an equivalent inverter representing the multiple areas. And we can then talk a little bit more easily about, well, what inter-area oscillations happen? What should we do with the inverters in the area to be able to suppress those oscillations? There's a refinement here that I won't go into, but it says there are some times when this process of forming an equivalent isn't just a matter of just add up the generators and lump them in the middle of the state. There are refinements to the ways in which we can aggregate. But by and large, actually within Australia, the aggregation process can be undertaken fairly naively and still come up with a very good representation of what does happen. Now, when you've got a three-area system like that, I'm presenting here one of the unifying themes for controlling systems is to say, all right, we've got these three equivalent machines. What we're going to try to do is suppress variations of kinetic energy. So we're going to try to come up with control strategies that looks at the rate of change of kinetic energy and try to design it. So this is V dot. We can expand that out, get the terms, and we say, well, what's the sensitivity of the total kinetic energy to the power injected by the photovoltaics? And the answer is, this is the rough shape. And so the control strategy, which gives us a nice strong suppression of oscillations, is by having the control roughly proportional to the velocity of the area. So we try to say we would be better off if there was a process that reduced the inverter injections when an area velocity is high. And the simple philosophy is represented here as a sort of ball rolling on corrugated iron, that there's a stable point at the bottom of the low energy, the low kinetic energy, and when the kinetic energy is kicked by a fault, we're trying to suppress that. So that's the simple concept of some of these controls. And we can form measurements, we can get a representation of what the angle of Victoria, the angle of Queensland is by running Kalman filters. But we'll ignore that for now. So overall, for control of a power system, the first step is to ensure all local modes are well controlled. Inter-machine oscillations, inverter oscillations. Once we've got our reduced model, then we can develop some control strategies for the inter-area modes. And in this case here, with this three-area problem, we design on the philosophy of the average area for the different groups. And so we come up with an oscillation set with no inverters. If we take our solar farms and say, well, we can't increase the solar power, but we can reduce it temporarily. So this can represent the change of power from the different solar farms. And you can see that there's a much stronger contribution to the damping by modulating these inverters. Once again, a hierarchy of models, which says we can come up with a detailed model for this inverter a detailed model for the phase lock loop, a detailed model for each of these. Once we're happy that this detailed model is well stabilized, then we can transfer it to this model to come up with a control design. So overall, series of steps, each step making approximations. The linear quadratic control, the inverters using local signals, is validated at the PSCAD level. Common filter design to infer the system Thevenin is done by modeling on a state average representation. We can reduce the areas to equivalent machines. Oops. We have a control design based on reducing kinetic energy and use Kalman filters to make sure that we're getting good up-to-date models of the system. So in summary, inverter synchronization dynamics have been a problem if we started from the idea of, while our only job is as a power electronics designer, synchronize to terminal volts. The power system guys will look after it after that. What we need to do is to get a little bit smarter, and so synchronizing to the inferred reference angle using a Kalman filter is a good way to reduce that interaction that's not very different from what we do at the moment. But if we have access to communication systems, then we can broadcast a reference angle and totally suppress any of these inter-converter oscillations, even in weak areas. So once the local modes are well controlled, then we can incorporate it on a system-wide control based on aggregate machines. So what's the takeaway? You can control power systems if you've got a mental model of what happens. To build the mental model, you usually want to have different levels of modeling, from the simplest phasor type representation through to a detailed validation representation. Once we've got all those together, then inverters are just another component within the power system, and their operation is not radically different in its contribution to system dynamics. So if you're wanting better frequency management, if you're wanting better damping controls, then considering these large inverters as simple systems and controlling them based on your overall plan is the pathway to salvation, even with reduced inertia within the states. Thank you all, and I hope you have enjoyed what I presented. One of the questions that's come up is, I've been talking about using inverters as controlling currents, and a number of people are starting to talk about grid forming converters. I haven't covered that very much. I haven't covered the grid forming converters very much here, but my perception is to use grid forming converters, you need local storage, and that's an additional cost and not needed. The other one is that we have got mechanisms of well-damped local modes with current controllers, and the grid forming converters of necessity do add additional modes to the operations that need suppressions. So I hope you've enjoyed the overview, and thank you, and we'll wrap it up at that point and invite a form of questioning managed by the managers.
Hi, Gerard. Thanks very much for the presentation. Very, very interesting, and yeah, definitely took me back to my uni days and to dust off a bit of understanding with what you were talking through there. I had one, and again, just open it to anyone who does have questions on the line, if you can post them in the chat window. But you mentioned, I guess, that sort of sequential process for building up or solving the micro problems and then building up to a larger level.
Yeah.
how, I guess, given some of the areas that these inverter-based systems are going into being very remote, very weak grids, how big of a problem do you see that local instability issue being? Do you see it as a major concern or something that's quite at hand to solve?
Okay, so if there was a very big solar farm connected into a weak area of the Queensland grid, then its phase lock loop will have problems to be able to inject at the right angle without its own variations causing synchronization problems. Now, if we broadcast the angle of Central Queensland to all inverters in Central Queensland, there's no possibility of oscillations, and the issue then is to make sure that our voltage profiles are maintained and that we can transfer the required power levels. So this process of weak grids is mainly a problem, well, for stability of phase lock loops. It's also a problem for protection. So for phase lock loop stability, I believe the solution is Kalman filters to infer a stiffer point or broadcast angles. For protection purposes, I am saying that we're starting to need a different philosophy of protection that says even if we've got inverter supports and that reduces fault currents, that does not mean that we cannot distinguish faults. But there's more work needed in that domain to make sure that the weak grid scenario is not such a boogeyman as it is at the moment.
Yeah, definitely. Thank you. Thank you very, very much for that. And I guess as a follow-up question, do you see, I guess, that role of publishing the phase angle across, for example, the state of Queensland? Do you see that as something that like AEMO would do, or the local utilities would publish out to the connected generators? This is the sort of phase angle we're running at, and this is what you should be synchronizing to.
Yeah. Traditionally, the detailed dynamic controls would have been the responsibility of the transmission company. And so I suspect that that would not be a bad management process. That, you know, but it's to form, if we wanted to know, well, what is the angle of Central Queensland? There may be 6 PMUs in the area that we need to amalgamate to come up with the best representation for then the appropriate broadcast.
I guess my question was leading down the path of, I guess, the independent operators for these renewable farms or battery systems, if they're playing in that CAS market. I was going to say they're probably a little bit more self-interested, and so I wonder whether it would be interesting to see whether you could come up with like a shared capability if they were installing sort of PMU style monitoring, whether they would be willing to share into a broader.
Yeah, I suppose the alternative is what is being experienced in Western Victoria, which says oscillations have the potential of developing, therefore I will constrain your 200 megawatt plant back to 100. If that can be avoided, I think that they would rejoice, the operators. So there is a win for them as well.
Agreed, definitely. Thank you very, very much for sharing insights on that. Kachan, are you on the line?
Yes.
I see we do have a few questions coming in. I'll hand over to you, mate.
Okay, thanks, Matt. So I can see there's a question coming, say, with control according to a calculated remote source reference encroach on inverter rating as PQ isn't controlled explicitly as the inverter terminals?
The injected current is being controlled at the inverter terminals. I would suspect that maintaining a a voltage profile is important, and that's why that was the point of my diagrams of phasors. So an overriding voltage magnitude would probably be a good idea, but the basic controls of magnitude of current is probably more robust than pure voltage control at the remote area, particularly when you're susceptible to oscillations. So in the weak grid, your terminal voltage is somewhat affected by your local conditions, whereas if your angle of injected current is reasonably consistent and stable, your voltage variation caused by the inverter would be suppressed, and it would be a sort of more steady state voltage management operating at a sort of outer level rather than the sort of fast management of current, which is happening at the moment.
I hope that answers your question. So there's another one. How robust is common filter estimation of the Thevenin equivalent phase angle reference to changes in the system impedance? So for example, light tripping and changes in power flow, inverters in the local area changing their output powers. Additionally, does network topology to which the inverter connects need to be known in advance for this method to work?
Yep. So yes, that's a potential weakness. There is an inherent robustness of Kalman filters, and so, you know, as with the LQR, the linear quadratic regulator approaches, there's a guaranteed stability margins. But if there are substantial changes of the network themselves, then it's a good idea to update your models. So my experience has been on the cases that I've studied to date of quite a high degree of robustness. So when we were designing our controllers for inverter number 9 here, it knew nothing about inverter 7 and 8. And you might say, well, that's unfortunate. We'd be a lot better off if we did. And the answer is the Kalman filter can still infer a much more stable voltage than we can from its terminals. So even if we took the voltage at this point and projected it 2/3 of the way up, our interactions, our sensitivities are much reduced than just working to the terminal volts. So I'm not claiming that there are zero issues for the Kalman filters themselves, but in this situation here, the Kalman filter for each of these things operating, ignoring some substantial variations from other inverters, is still working quite robustly, and we can get a much more stable operation than if we were just working to the terminals. So the Kalman filters, you can come up with ways of having pre-configured changes if you know that there are sensitive configurations then designed to those. But what we're saying is that the concept of inferring a stronger voltage point isn't highly dependent on the exact model being used. Like at the moment, when we're controlling inverter 9, we know nothing about the rest of the network and we suffer the consequences. The Kalman filter reduces those consequences, and even if some of those impedances do change, as long as we were trying not to be too greedy about backwards inferring, we can still substantially improve the robustness of the network. Right? It's a choice. It's our choice how far to back project, how far to track our inferred Thevenin volts. but the evidence to date has been of a substantial increase of robustness over just using terminal volts.
Yeah, I think they're definitely a step forward than just using the local voltage. So it's better, definitely better than local voltage. And plus, there are also the broadcast reference signal that could help.
If you use the broadcast, then you're, in a sense, not dependent on any Kalman filter modeling to be able to know what you should do.
Yeah. So I also have a question. So I think since you're talking about the grid forming inverters, I think I want to think about grid forming inverters. I say there's still a gap to synchronize all those grid forming inverters. I think your approach is definitely connecting, bridging the gap here. So how to synchronize the grid forming inverter with those grid falling inverters in the network.
I mean, if inverter 8 was a source of voltage that we tell an angle to, right? I mean, a grid forming inverter chooses a voltage and chooses an angle. And oftentimes the angle updates are based on power flows, so it can pretend to be a synchronous machine. But you can see that we're introducing a new set of synchronous machine oscillations potentially by using grid forming. Doesn't mean that we can't broadcast a reference angle for the grid forming to actually track. And I think that would then bring them into the fold as being stable local oscillations.
Yeah, thank you, Gerard. So there's another question. So in Western Victoria, what sort of instability were of concern? Are they PLL interactions between generators in the area? What sort of frequency were unstable?
Okay. My understanding is that Northwest Victoria is fairly weak and the lines have got multiple converters connected along them. So something more like this string that we're talking of here. And what would happen is that the phase lock loops for the different inverters would start to wobble the connection point of 9, which wobbles the connection point of 8, which then creates dynamics of the phase lock loop. So typically, I think the 6 to 10 hertz is what has been tended to be seen. And so to avoid that, you say, well, this risk of instability that we saw here, as the line impedance increases or as the power flow along those lines increase, these eigenvalues become less stable in the raw system. And the frequency does tend also to decrease somewhat as well. So we might have started off with a fairly well-damped 10 hertz oscillation possibility here. We then double the line impedance or double the power transfer. You can see that the eigenvalues get much less stable and become lower frequency and hence more potential interaction with the synchronous machines. And so that's been the concern in that area. And it all comes down primarily to the phase lock loops that are being used. But it's not as saying, well, what we need is just better gains on the phase lock loops. I'm saying, actually, no. The concept, they're doing a damn good job at the moment, as far as you can. What you need is a better reference to lock to, rather than a better locking process.
Yeah, I believe that's a very good answer. So there's a very good question. So would it be fair to categorize this approach as prioritizing stability at the expense of a local voltage control? Currently, inverter must deliver high gain local voltage control, which could possibly contribute to the instability.
Okay. High gain local voltage magnitude control is not the inner loop. The inner loop in most inverters is current control. The adjustment of the reference as an outer loop achieves a degree of voltage management. The same potential possibility exists here, that the inner loop is controlling the current to the broadcast angle, and then you have an additional term potentially to control voltage magnitude. In these diagrams here, controlling the angle of current essentially controls the magnitude of terminal volts. And so we might have a broadcast angle of VS, but then modify it for the sake of local terminal volts. But you would be able to much more easily put limits on it to be able to manage that as a slower outer loop, with the fast loop being the current, following the current reference.
Yeah, thanks, Gerard. So the next question is, are you planning on benchmarking those approaches on more realistic examples? For example, looking at actual weak area of the network in Australia, or including communication delays for reference angle broadcast type approach?
I have no researchers employed on this. I am reducing my hours of working. There will be no progression of this without funding of research. We're trying at the moment to have funding through the Australian Research Council. We're trying to promote this particular research as an Australia-China research project, but it's all dependent upon funding of research. And so validation is important. One of the issues with validation is that a lot of the detailed models are hidden from academics, and as such, precise validation is actually not available to me. And it would be best done in a collaboration.
Yeah, I agree. Yeah, I believe there's the collaboration opportunity will be benefits to both parties. Last questions to Gerard. So I see a lot of utilities are using a fault level to assess the weak rates, to assess how much solar farms or wind farm you can build in there. So can you elaborate on your understanding of the short circuit ratio, and if your control approach could actually loosen those requirements, because you are inferring those voltage to a further away or using broadcasting goods? So is that means we could actually loosen those requirements? Yeah, thank you.
I think we've got to be careful about the word about weak grids. Here I've been using it as a Thevenin impedance type term, but when we're dealing with operations and oscillations, that's usually a small signal term, and inverters can help strengthen grids in the small signal. So the effect of strengthening by control of inverters is quite feasible and possible and should be used. Fault levels are a different thing, right? So there's the small signal weakness, and then there is the large disturbance weakness, large disturbance weak grids. And it's the large disturbance weak grid model that's being used mentally as a way of describing what's weak, and not necessarily looking at the support that is potentially available through inverters for small signal weakness. So small signal weakness can be overcome by having voltage support mechanisms. And so we don't need to use, well, we shouldn't be using the same word to describe small signal voltage variation and large disturbance current magnitude. It's a convenient way of saying if the system was strong, if the impedances were very low, we would have none of these problems. Absolutely agree. As a way of characterization, how much can we make this system better? These disturbances I've been talking of are essentially small signal disturbances, and inverters are in a good position to manage small signal disturbances. And so the weakness of the grid can be asked in two different ways and should be answered in two different ways then.
Yeah, thank you, Gerard. I think that's most of the questions, and I head back to you, Matt.
Thanks very much, Kachan, and yeah, really interesting insight there, Gerard, on the potential for oversimplifying that. Something I can consider. I'd probably and nominally think of strong or weak grids based on a fault current or an impedance value, but as you say, it's definitely more detailed than that. So Gerard, I'd like to, I guess, again say thank you very much for your time. It was a very, very interesting and extremely detailed presentation. As I said, definitely have to go back to my university understanding to probably fully understand some of what you've spoken about. But look, it's evident that it created a lot of interest and a lot of discussion in the questions that we did get. So thank you very much for your time. For those that are on the line, I will quickly put up the NGN's details again, and Professor Ledwich's details. So if you want to get in touch with Gerard, his contact details are on the side. I'll leave them on for a little bit after the end of this meeting. Please obviously do be respectful. He's an extremely busy man, and so it may take some time to get back to you. And if you do get in touch with either the NGN or Gerard on anything relating to this question, if you can just preface the subject with something that makes that quite obvious. So again, thank you very much, Gerard. Really do appreciate your time and yeah, for the very thought-provoking presentation.